Okay, if everybody's ready, that's the stream just going live on YouTube. So once that's all set, I'll give you, yes, there we go. We can start the session. Enjoy.
Oh, all right, welcome everybody. Good morning, good afternoon, good evening, good night, whatever it is. Welcome to parallel session 2 out of 2 for LISA Astrophysics. My name is Gijs Nederlands. I'm an astronomer from Radboud University in Nijmegen in the Netherlands. We have a very full session, so we will start very soon. But before we do so, let me introduce this session. We have a very diverse lineup. We start this session with 3 talks by Shen Chin, by Sophia Yi, and by Shuyan Lao on different aspects of astrophysics, and we'll come back after a break. As many of you will by now know, please ask your questions in the chat at any time. We'll only look at them at the end of the presentations. You can also add your questions in the live stream chat. This will be monitored. I think that's everything to be said before we start. So without further ado, let me introduce the first speaker. Shen, please go ahead, share your screen, which is Shen Xin from Columbia University, talking about ultra short period massive black hole binary candidates in LSST, as these are verification binaries. All right, go ahead.
Okay, thank you for the introduction. So can let me know if you can see my slides in advancing.
Yes, and we can hear you. So go ahead.
Great. Okay. Thanks for the introduction. My name is Chengcheng Xin. I'm a graduate student at Columbia University. So thanks for the organizers for giving me the chance to present my short project. So this work is in collaboration with Zoltan Hyman, also at Columbia University. And our work is trying to predict the number of massive black hole binary candidates in LSST and the number of binaries that we would see in LISA as verification binaries. I'll explain what this term means in the upcoming slides. Okay, so we all know that LSST by Vera Rubin Observatory is going to launch in the mid-2020s, hopefully. And among many of its benefits, it's expected to discover a large sample of quasars, likely in the order of tens to 100 millions. So, and as we know that quasars are triggered by merging galaxies, so almost all of these LSST quasars might be powered by inspiraling massive black hole binaries. And among these quasars, a tiny fraction of these could be eventually evolving into the LISA millihertz frequency bands. And as it turns out, I'll explain later the reasoning, most of these have ultra short periods, typically of less than a day. So we call these quote unquote verification binaries. You can think of them as analogous to the galactic white dwarf binaries, which we know LISA would catch, but they're obviously different because they're massive black hole binaries. So the goal of this work, the first goal of this work is to compute the number of quasars predicted in LSST using the quasar luminosity function. So for this, we use a recent work by Garish Kulkarni et al. 2019. We use this work because it's a very large compilation of quasar data from almost all of the major optical surveys. So their quasar luminosity function takes the form of double power law, which is characterized by 4 parameters. So here we have the normalization parameter phi star, a breaking magnitude m star, and 2 slopes, a bright end slope and a faint end slope, alpha and beta. So all of these 4 parameters are redshift dependent. So to get a smooth quasar luminosity function, we interpolate these 4 parameters at 50 values of evenly distributed values of redshifts. So finally, quasar luminosity function can be quasar luminosity can be directly related to the black hole mass under some key assumptions, including but not limited to F Eddington equals to 30%. We also assume a standard quasar spectral template. And last, we assume that the fraction of quasars associated with massive black hole merger is approximately 1. Okay. So these are the first set of results from the interpolation. Our results are in the solid black curves. So this plot shows the number of quasars in LSST as a function of redshift for 11 different magnitude bins. So for comparison, we also add the numbers predicted from the fiducial Kulkarni et al. Luminosity function in the dotted black, and also the numbers presented in the LSST science book. So that's the dotted blue line. As you can see, most of these curves agree with each other, especially in the most relevant region, and that's between redshift 2 to 3. However, for the fainter magnitudes, due to the lack of data coverage, the data coverage is very insufficient for the fainter magnitudes. We had to extrapolate the quasar luminosity function to get the estimates. And finally, I want to mention these sharp cutoffs are just due to selection effect in the original quasar catalogs being used to obtain these luminosity functions. Okay, and so just to summarize the last page by words, from redshift 0 to 7, we predict that LSST can identify 20 million quasars, assuming a single night LSST exposure, and that is from I magnitude of 16 to 24. But if LSST is able to collect their data to lower the detection limit down to 26, we might be able to expect 100 million quasars. But there's two important points that I want to bring up, or two important caveats, as you may call it, that's relevant to this number. So first of all, there are uncertainties that comes into N, and most of this uncertainty comes from the uncertainty in quasar luminosity function. And also the lower detection limit of LSST can be achieved, but it's a little bit harder to achieve by co-adding the light curves over a longer period of time. So these 2 points, I don't have enough time to get into it in this short talk, but I encourage you, if you're curious about either of these caveats, you should check out the paper for the corresponding discussions. Okay, so we finally get to LISA. So the goal is to find the number of compact binaries that could be caught in LISA. So for this, we use the LISA signal to noise. I'm assuming you all have seen this curve in some form. So here I use the curve from Robson et al. 2019. I also demonstrate some evolution of binary black holes with primary mass of 10 to the 7, 10 to the 6, and 10 to the 5 solar mass, where I assume the binary mass ratio is 0.1. So in each of these 3 tracks, the redshift are 1, 3, and 5 from top to bottom. And the diamonds, I believe, from left to right are 1 year, 1 month, and 1 day to merger. So for the binaries to be caught by LISA, or eventually evolve into the LISA band, it has to be above this curve. Otherwise, if it falls below in the region, in the orange circle, it could be caught by, it could be identified as LSST sources, but it wouldn't be caught by LISA. So just for reference, I pointed out the observed frequency corresponding to a period of 1 day. So another important assumption in this is that we assume at least a lifetime of 5 years. And this could be obviously stretched out, hopefully up to 15 years, depending on how long LISA flies. And that just comes from the fact that LSST launches in the mid-2020s and LISA launches in the mid-2030s. So this just means the time that the quasar is caught in, that the quasar is detected in LSST has to be 5 to 15 years prior to the LISA detection. So to find the exact number of verification binaries, so the verification binary just refer to the ones that we're able to catch by LISA above this detection curve. So to find this number, we assume a very simple model. So the fraction of LSST quasar that will enter the LISA band is simply scaled by a fraction of Tm over Tq, where Tm is the time to merger, and this follows the concept that I just introduced, which is LSST should catch the quasar in the last 5 to 15 years of its lifetime. And the lifetime of quasar is on average 10 to the 7 years. So it follows simply from this, this fraction that the number of verification binary is just Tm over Tq times times n cursive n, the number of quasars in LSST. Okay, so the number of verification binary here are presented as a function of redshift and black hole mass, which is directly converted from the magnitude. And this is the most ideal case scenario where we assume a time to merger of 15 years. So TM equals to 15. So most of these binaries are concentrated in a region from redshift 2 to 3. And this is consistent with the fact that the quasar luminosity function actually peaks at z equals to 2 to 3. And also most of the sources have are on the lower mass end. So from 10 to the 5 to 10 to the 6 solar mass. And this is because the faint end of the quasar luminosity functions are very steep. So in fact, how many quasars were able to, how many binaries were able to see as verification binary depends mostly on how deep LSST can go. So the detection limits, as I marked with the black and the 2 gray lines, corresponds to the single night exposure of 24 and down to 26, which is possibly the lower limit that LSST is able to achieve by co-adding the data. So depending on the lower limit of LSST, we might be able to get 30 to up to 150 verification binaries in LISA. So this plot just shows n as a function of z and m, but it's also a function of period, which in my opinion is also a very interesting parameter. So in the last page, we saw the ideal case scenario where TM is 15 years. So here on the right-hand side plot, I calculate the period of, these are the distribution of the periods of these verification binaries, and also for the least ideal scenario where TM equals to 5 years. But in either of these distributions, we see that the majority of binaries have really short periods, typically within 1 to 2 days. And you can see this more clearly in the zoomed in figure on top. So what does this mean? So this is a very interesting result to me, because overall we see that from this work, we're able to see a handful of ultra short period massive black hole binaries in LSST among a very large group of quasars in the size of 10 to 100 millions of quasars. So these are what we call the needle in the haystack quasars. And what's interesting to me is with years of observation, we might be able to see the evolution of periods, possibly from days to hours. And this is a very robust evidence for the existence of these verification binaries, because this would be during the gravitational wave driven phase of these massive black hole binaries. So this comes to the end of all of the results. Oh, and one more thing I wanted to mention is that obviously this is the most ideal case scenario. In reality, LSST has to try way harder to identify these short period binaries, especially since we can see the evolution of the period even over a few years of observations. So to summarize the talk, first of all, we found that LSST can discover 20 to 100 million quasars with masses of typically 10 to the 5 to 10 to the 9 solar mass, and redshift from 0 to 7. And among these LSST quasars, 10 to 150 of these could have ultra short period and could be detectable in LISA if they were caught by LSST in the last 5 to 15 years of their lifetime. So to make the result better or to improve on the existing quasar luminosity function, we need just better faint end slope for the quasar luminosity function, either by obtaining more data or develop a more a better statistical extrapolation for the luminosity function to reduce the statistical uncertainty in the luminosity functions. And next, we can also co-add the LSST data to search for more fainter sources with ultra short period. So next, I pointed out the needle in the haystack problem, which comes in a bonus in this project, that if we see the chirping of the period for these verification binaries, we could this is a robust evidence of the existence of these binaries. And last, which I have not mentioned before, is that given existing LISA detections in the future, or even any sort of evidence of LISA alerts could reverse this work, and they could guide the search of periodicity either in the archival LSST data or any other major upcoming surveys with electromagnetic signatures of the quasars. And that's it. So thank you for listening. If you have any questions, either you can bring it up now or ask me with email. I believe it's on the program.
All right, thank you very much. Well timed, plenty of time for questions. I already see a first hand. Astrid, please go ahead. If you can. Yes, you can.
Yeah, yes. I find this very interesting. I don't know much about massive black holes, so I'm just curious, how long do you think LSST will need to be observing before we start seeing the first of these candidates? And then the follow-up question would be, if we actually want to find them, which is a major challenge, is this something, you know, someone from the community needs to do with all the data set and somehow make it work? Or could we include some of these searches in some of the LSST brokers, for example? Because I know some people are working really hard to make algorithms that actually search for things efficiently. I don't know how they work, but I wonder if we could include this over there.
Yeah, so there's two directions that you could go. I think I could answer both of your question at once. Let me try that. So the first one is, first of all, I pointed out to identify the period of these short period quasars is challenging in the first place. The quasar with shorter period can actually be harder to confirm than those with longer period. I think LSST right now plan to have 3 exposures per night. So this is already longer than the predicted verification binary period that we're looking at here, which is hours. So it would require a lot of co-adding to confirm the periodicity, but we can't have too many data so that we introduce additional statistical uncertainty. So that's something I guess LSST scientists could do. And then in the reverse direction, I think once LSST identify these, could have some of these quasars could have the short period and the mass that's within the range that we roughly predict here. We could say that, oh, these could be potential LISA sources for LISA to point in the future. And in reverse, if we identify something in the LISA detection, but we're not able to, we weren't able to focus on these in the LSST catalog, we can use that as a reverse search for their ENM signatures in LSST or other surveys.
Thanks.
Yeah.
Are there any other questions? I don't see hands or anything in the chat. In the meantime, I had a question. Suppose we find the periodicity, do we immediately have some idea about the masses, I guess the distance, yes, but also about the masses of the black holes? Or would that be unknown and we need to get the F dot or the period change to get the masses?
So the mass can be inferred from the luminosity as a first step if we know the redshift. So that's directly how I would, I guess, obtain the mass. Yeah, I'd say we would directly know the mass.
Okay, that would be great.
Yeah.
I see no more questions. I want to comment, not meant as a criticism, but I think with verification source, I think maybe it's better to call it sort of pre-warning or whatever thing, right? Because I think one of the things that's interesting now is that data analysis people should wonder, what if there is a LISA source where upfront we know the distance and the masses and the sky position? Nobody, I think, has really wondered about that. They work very hard to get the sky position to alert EM people, but this is the reverse order. Anyway, thank you very much for this question. Let's thank Sheng again. And so we switch gears a little bit, at least in terms of, I guess, size and distance. We move to Sophia Yi from University of Virginia, talking about determining the individual masses of accreting white dwarf binaries. Please, Sophia, go ahead.
All right. So hello, everyone. I'm Sophia. I'm an undergraduate student at the University of Virginia. And today I'll be presenting my research with Professors Yagi and Aris on determining the individual masses of accreting white dwarf binaries. So the type of binary white dwarf systems we're looking at are depicted in this image on the right. We have a donor star, and although it's larger in size, it actually has a smaller mass. And in particular, we're considering donor white dwarfs with that are called really extremely low mass donor stars, which means they have this helium core and may or may not have a hydrogen envelope as well. But the picture to keep in our minds is that we have this extremely low mass donor white dwarf that is losing mass or accreting onto its binary companion, which I'll refer to as the accretor throughout the rest of this talk. And so when we first set out to do this research, we were really interested in just seeing if we could tell what the masses of this donor and the accretor star are using LISA's measurements of the frequency and frequency derivative of gravitational waves emanated by the binary. But along the way, we ran into some issues and ended up having to tweak our technique in a way that had us actually kind of add studies on the measurability of a few other white dwarf parameters. So I'll talk about that extensively in a bit, but just to begin, I want to describe our approach to the problem. So we begin with the understanding that the gravitational waveforms collected by LISA can be broken down into an amplitude, which I'll call A, times the cosine of a time-varying phase called phi. And the idea is that we can further break down A and phi into measurable quantities. So we're looking at the gravitational wave frequency derivative, so that's F and F dot, and then also the luminosity distance D and the chirp mass script M. And the idea is that the more that these parts, these measurable quantities in the waveform depend on white dwarf parameters, the better we'll be able to measure these parameters. So for instance, if we have a way to express the frequency entirely in terms of the donor mass, then anytime we receive LISA's measurements of frequency, we'll immediately be able to infer what the donor mass is. Now, of course, this is a very simplified picture. In general, F and F dot are going to depend on more than one white dwarf parameter. And so let's see what parameters they depend on. So expressing F and F dot in terms of these white dwarf parameters, what we do is we begin by considering the particular mass accretion mechanism that exists for these types of binary white dwarfs. So for the extremely low mass white dwarfs that we're considering, accretion occurs through what's called Rauschenlob overflow. So the Rauschenlob is what's shown here in the kind of light blue dot dash line. It's the outer limit at which matter is gravitationally bound to the white dwarfs. And what happens in Rauschenlob overflow is that the donor star expands over time due to evolutionary pressure, and it ends up filling its portion of the Rauschenlob and then kind of overflowing and seeping into the left portion where the binary companion is, and matter becomes gravitationally bound to the companion. And so if we have this particular mechanism, if we have Rauschenlob overflow or Rauschenlob filling, then we actually know that the donor star's radius will scale with the semi-major axis. And so we can throw this kind of proportionality into Kepler's third law, where we have the frequency is 2 over the orbital period. And then we arrive at a very simple expression for the gravitational wave frequency in terms of just the individual masses and the radius. Then what we can do is we can differentiate this relatively simple equation for F with respect to time to get F dot. And when we do this, because of the way that the radius and the mass are related, we end up introducing this new parameter called eta. And I'll explain a bit what eta means here. But the idea is now we have F and F dot in terms of just our our white dwarf parameters, the masses, the radius, and then eta. I'll mention that this expression for F dot assumes that no mass is lost from the binary due to shell flashes or anything like that. But yeah, so here we have F and F dot. But what is eta? So essentially, eta defines the response of our donor white dwarf to mass loss. And what I mean by that is that eta will tell us whether and to what extent the white dwarf will grow or shrink as we take mass away from it. So for the extremely low mass white dwarfs we're considering with these helium cores, eta depends very drastically on the stage of evolution we're considering. So in an early stage of evolution, The white dwarf has a helium core, but that helium core is surrounded by a thick hydrogen envelope. And what that hydrogen envelope does is that it causes the star to behave like ordinary matter, in the sense that as we remove mass from the star, it will shrink. So this kind of intuitive phenomenon of the radius decreasing as mass decreases corresponds to eta being greater than 0. And this is to be contrasted with the late stage of evolution, where the hydrogen envelope has been stripped away. All we have left is the degenerate helium core. And since this star is now degenerate, the radius will actually increase as mass is lost from the donor, and this corresponds to eta being less than 0. So what we expect then is that as the star transitions from an early to a late stage of evolution, this parameter eta is going to start at some positive number and then eventually pass down through 0 and enter the negative regime. It's worth mentioning, although the early stage of evolution doesn't last for nearly as long as the late stage, we're definitely still interested in studying this early stage of evolution, because this is when the emitted gravitational waves by this binary are expected to be largest. And so we have a greater chance of being able to detect white dwarf systems with donors in this kind of early stage of evolution. It turns out that considering this difference between the early stage and the late stage of evolution does more for us than just tell us what eta will be. And what this comes down to is the fact that in the late stage of evolution, we actually have an analytic mass radius relation given by P.P. Eggleton. And so because we have this mass radius relation, anytime we have a donor mass value, we'll also immediately be able to infer the radius of the donor star. And then because of the way eta is defined, we can rewrite eta as the mass over the radius times the derivative of the radius with respect to mass. And we have, since we have an analytic formula to throw into this derivative here, essentially what that means is that anytime we have a donor mass value, we'll also be able to immediately infer the radius and eta as well. It turns out that we can also immediately infer the gravitational wave frequency from just the donor mass in this late stage of evolution. This can't be immediately seen from the equations, but it was first observed in this paper by Breivik et al., where they simulated a bunch of these binary white dwarf systems with the extremely low mass donor stars, and they observed this universal relation between the donor mass and the frequency. And so what we did is we took the analytic mass radius relation from Eggleton, we threw it into the frequency expression that I derived on the previous slide, and we found that we were able to replicate Breivik's fit. And so their fit is showed in the dashed black line in the background, and then we have our plots of the donor mass with respect to frequency for a number of different accretor masses here, and we see that the curves all agree very well. And so what this means then, just to kind of summarize this slide, is that anytime we have a value known for the donor mass, we immediately will also know the radius, eta, and also the frequency. And so in this late stage of evolution, there's a really nice way to kind of tie together all these parameters and see how they're related to each other. And this can't be done in the early stage of evolution. So to begin with, we don't have an analytic mass radius formula for the early stage of evolution. And we thought, well, maybe we can find some way to relate the mass, the radius, and eta using experimental results. So we turned to MESA, which is a public stellar evolutionary code. And we started modeling a bunch of white dwarfs with helium cores and hydrogen envelopes. We tried different sizes of helium cores and envelopes and such. And we started trying to interpolate this data for the radius versus the strip mass, as well as eta versus the strip mass. Unfortunately, what we found is that it looks like the radius isn't computed to a high enough level of precision with MESA for us to be able to take the derivative. And we end up running into all this kind of very unphysical noise. And so what I plot here is the absolute value of eta on log scale. And so we see that eta starts positive like we expected. It dips down through 0, which is where the cusp is, and then enters kind of the negative regime. But then we run into all this noise. And it turns out that this is actually one of our better models. And often we would run into noise before eta even reached 0. And so what this means then, in terms of minimizing the amount of parameters we necessarily have to look at in our parameter estimation, is that in the late stage, it looked like we might be able to do our estimation with just 4 parameters: the initial phase, the 2 individual masses, and then the luminosity distance. However, since we can't relate eta, the radius, and the mass together very neatly in the early stage of evolution, we have to now include eta and the radius in our parameter set. And then, of course, since we want a very holistic view and we want to perform our parameter estimation for the early stage all the way into the late stage of evolution, we're going to have to use this larger parameter set. And so, as you can imagine, performing a parameter estimation with 6 parameters is going to be a little more difficult. Fortunately, one thing we may be able to do is eliminate one of these parameters. And specifically, we might be able to take away D as a parameter. And we could do this if we assume that the luminosity distance can be independently measured by a different detector like Gaia. And if that's the case, if we know D, then obviously we don't have to include it as a parameter. And then we have we have just this 5-parameter set. And I wanted to show this plot by Breivik et al., where they have estimated that there are a number of these kind of binary white dwarf systems with the really low mass donor stars that are expected to be detectable by both LISA and Gaia. And so it's not completely implausible that we would be able to remove D as a parameter. So now we have what our parameter sets will likely be, and I'm going to explain what the parameter estimation is that we did. So we really just performed a Fisher analysis, and the way that this Fisher analysis works is that we define the Fisher information matrix so that each of its elements are computed as the inner product between partial derivatives of the waveform with respect to each of the parameters of interest. And then what happens is when we invert this Fisher matrix and then take the square root of the elements, we receive back the uncertainty on our parameters. And so I'm going to show our results for the Fisher analysis for both the 5 and 6 parameter set, including and excluding D. But first, I just wanted to show this plot of the gravitational wave strain versus LISA's noise curve. So again, we have the noise curve from Robson et al. And the gravitational wave strain curves are the ones in the green, purple, cyan, and brown. They start where the orange arrows are pointing. They evolve up to the top right where they reach a period minimum. And then they enter the late stage of evolution, which is the kind of long tail extending down to the bottom left of the plot. And so what we see here is that, especially in the early stage of evolution, like I mentioned earlier, our gravitational wave strain is much higher than LISA's noise curve. And so we have a good chance of being able to detect the binary white systems, particularly in this early stage. So now we know that, yes.
3 more minutes.
Okay, thank you. So now we know that we should be able to detect the gravitational waves from these binaries. And then now that we know that, let's see what we can see with these gravitational waves. I'm first going to present our results for the 5-parameter set. Again, this is here where we assume that the luminosity distance has been independently measured. We actually assume that it's been measured to be 1 kiloparsec. Again, we use LISA's noise curve from Robson et al., assume a 4-year observation period. And then because we have so many parameters, we actually had to impose some Gaussian priors on the masses. And specifically, we have a 0.1 solar mass range for the low mass donor star. And then we believe that the accreting companion is likely to be a carbon-oxygen white dwarf that exists in the roughly 1.2 solar mass range. So with these as our assumptions, here are the contour plots that we get for the fractional error on the individual masses. What we have here, the way to interpret these plots is we're looking for a small fractional error, because a small error, of course, corresponds to being able to measure the white dwarf's masses to a higher level of precision. So we see that particularly in the blue and purple kind of region of parameter space, where the white dwarf and the where both masses are kind of higher masses within our range, we see that the fractional error is pretty small. And this means we have a very decent chance of being able to constrain the individual masses in these regions of parameter space. We find a similar thing for the radius and eta. In particular, eta looks very well constrained. We have very small or relatively small errors on the donor radius. And then the measurability of eta also looks fairly good if we focus on this kind of purple blue region of space again. And so to summarize our results with the 5-parameter set, as long as we know the luminosity distance and we impose the priors I showed, we have a very fair chance of constraining both the individual masses as well as the radius and eta. Now let's see what happens when we add D as a parameter into our set. So again, this is where we assume we don't know the luminosity distance independently. The rest of our assumptions are the same. And what we see,
one more minute.
Okay, what we see here is that unfortunately, when we don't know D, the parameter estimation simply returns the priors on the masses. So we gain no additional constraints on what the individual masses will be, which is unfortunate. On the bright side, as we can see here, the radius and eta are still relatively well constrained. In fact, if we compare it with the results for the 5-parameter set, we see that our error is about the same. It hasn't changed even though we added luminosity distance as a parameter. So to summarize our findings with the 6-parameter set, we are unfortunately unable to kind of constrain the individual masses in this situation. However, we are still able to measure the radius and eta to a roughly good extent. And then to summarize everything then, to wrap up what we're doing here, we used a Fisher analysis to estimate the measurability of a few white dwarf parameters, first the masses, and then we also ended up including the radius and eta. And what we found is that if we know the luminosity distance independently, we have a fair chance of constraining all 4 of these parameters. But unfortunately, if we do not know what the luminosity distance is, then although we can still kind of measure the radius and eta, unfortunately, we are no longer able to constrain the individual masses, the mass of the donor star and the white dwarf and the accreting star. So that's all I have for today, and I'd be happy to take any questions.
Thank you, Sophia. Well timed. Are there any questions? There is a question or more a comment in the chat by Dennis. Do you want to unmute and say the comment or ask a question?
Oh, yeah, it might or might not be a problem because the error in the Eggleton formula is about 2%, but it also fluctuates quite rapidly up and down as a function of mass ratio. So it's not a smooth approximation to the exact calculation. The power law, I mean, I'm not sure. The only way to tell is to use a more accurate formula and compare. It might not be a problem at all. I don't know what the other errors are. Maybe other errors are more than 2%.
Yeah, I'm not sure. We've only tried using Eggleton's formula. One thing we did is we computed eta with Eggleton's formula, and it came out to be roughly what we basically modeled a few curves, and when we used Eggleton to compute eta, it came out to be eta equal to -1/3, which is kind of what we expect. I guess that's kind of by definition that for Eggleton's formula, we have the cold temperature formula. I'm sorry, I don't know of any alternatives we could use that might be more accurate. But yeah.
Well, there are ones, but instead of power to the 2/3, you have slightly different powers or better. So you have a 2/3 and a 1/3, but it turns out that if you adjust those numbers, you can improve it. And then there's other ways, just by including more terms in the expansion, you can improve it too. But if it's not just a simple power law, it might mess up the simplification.
Yeah, and I'll just say this is why we were interested in trying to use MESA to model like radius and mass curves, because ideally we'd be able to see what actually happens like from experimental data if the radius or if eta reaches -1/3 or some other value. Just being able to confirm that with MESA would be nice. So we're still working on that. We're still trying to tweak our approach with MESA, see if we can get rid of that noise.
Yeah, I think the mass radius is probably more uncertain for the comparative. Yeah, okay.
Let's wrap that up. There is a question, I guess, from the YouTube. Why is the blue-purple area your lowest errors? Please, could you go over that?
Sure. So that's really just a function of how I've the particular color plot function on Mathematica I use. It's just the color plot is just the scale we have. So the red corresponds to kind of the smallest fractional, or sorry, the largest fractional error. If we go 10 to the minus 0.35 is going to be a smaller error than 10 to the minus 0.05. So that's just
I think the question is, why are the blue areas in the regions where they are? You already explained it for the left one, I think, right? Because of the higher masses.
Oh yes. Oh, okay. Sorry. That makes more sense. Yeah. It's a function of. So really, what it comes down to is for the donor mass, when we have a higher donor mass, again, because especially in the late stage of evolution, it's really the donor mass that's determining the frequency. Then we're able to constrain these mass higher, to a higher level of precision. I will just show. I didn't have time to show this in our actual plot, but what we found is that we could actually trace where the error on the radius and eta and d were coming from. And if you look at plots of the derivative of the frequency with respect to the radius, or the f dot with respect to eta, and then we also include the SNR, we almost completely replicate the shape of these contour plots. And so what this means is that basically we know that the error on the radius and then eta and then d, those are all determined by different portions of the amplitude. So for radius, it's f and then SNR. If for eta, it's like f dot and then the SNR. And then for the luminosity distance, it's a question of how well we can constrain the amplitude. If we take the derivative of the amplitude with respect to d, that's where we have these kind of shaped contour plots.
All right, in view of the time, we have to wrap up. Thank you again, Sophia. And we move to the third talk of this session by Shuyan Lau, also from the University of Virginia, on the effects of dynamical tides on gravitational wave signals from eccentric double white dwarf systems.
Right. Thanks for the introduction. So, hi everyone, I'm Shuyan Lau. I'm a PhD student from the University of Virginia as well. And I'm from the same research group as Sophia. I'm also working with Professor Phil Aris and Ken Yagi. Today, I'm going to share with you this project we have been working on and about the effect of dynamical tide on the gravitational wave signal from eccentric double white dwarf systems. So we are kind of wrapping up right now and writing a paper. And if you are interested in this topic, please stay tuned. So first of all, I would like to talk a little bit about the motivation of this project. So in this project, we focus mainly on detached eccentric double white dwarf systems within the LISA frequency band. And we want to study the effect of dynamical tide on orbit and hence the waveform. In particular, what we find is that the dynamical tide has two main effects on the orbit. First one, if the dynamical tide effect is perturbative on the background orbit, then it will cause the orbit to have extra orbital precession. And for orbits with higher eccentricity and small separation, we find that the dynamical tide kind of drives the orbit into chaotic motion, which completely alters the waveform. So why are we interested in these eccentric systems? So as we all know, this galactic double white dwarf systems is one of the most promising guaranteed sources for LISA. We're expecting around 10,000 of these systems to be detected. However, most of them, due to their formation method, they're kind of circularized before they even form. So in order to have these eccentric systems, we require multiple body interactions or dynamical interactions. And these have been studied by some previous literature. For example, for these ones by Ivanova et al. Or Williams et al., they have estimated the eccentric double white dwarf systems come from the globular clusters within our galaxy, and they're expecting at least a handful of these systems to be detected by LISA. And for multiple body interactions, unfortunately, these populations are kind of poorly constrained, but within these systems, there is the so-called Kozyladov mechanism that drives the system into high eccentricity and forming eccentric double white dwarf systems. So what makes these eccentric binaries interesting is that they have a very different waveform from the circular ones. As illustrated in this equation here, the waveform basically composed of a sum of harmonics. And as illustrated in this plot in the frequency domain of the waveform, basically the waveform of an eccentric binary consists of a sum of harmonic represented by each peaks here, and they have the eccentricity dependent amplitude and also a precession term in the waveform, which splits each harmonic into 3 different submodes. And by measuring the relative amplitude of these harmonics, we can know the eccentricity of the orbit. And by measuring this splitting, we can know the precession of the system. So this is actually discussed before in a study by Williams et al. In 2008, which they consider the precession due to various non-Keplerian forces on the eccentric double white dwarf systems. And in particular, they considered 3 different effects: the tidal effect, the leading post-Newtonian effect, and also the rotation effect. For the equilibrium tide effect, they consider the formula using the tidal Love number, which the equilibrium tide depends linearly on the tidal Love number and have a 1 over the separation dependence to the 5th order. And by measuring this tidal precession, one may actually infer some information about these tidal parameters, which it depends on the internal mass distribution inside the white dwarf. So the thing about this equilibrium tide formula is that it is basically the static limit of the general tidal problem, which has ignored the dynamical tide. So this kind of motivates us to think about what the dynamical tide can give us inside the eccentric double white dwarf systems. So now, in order to solve for the dynamical tide, we'll have to consider the full tidal problem, which basically we have to solve simultaneously the equation of motion for the fluid element within the star, and also after the deformation, the extra force that the deformed star gives to the orbit. So in order to solve the problem, we'll need to solve for the deformation factor C, and a useful method is to decompose it into a spaces formed from its eigenmode with eigenfrequency omega alpha. In order to simplify our calculation, we consider only the dominant mode, the so-called F mode, which has the largest overlap integral with the tidal interaction. Right. So with this approximation, we consider the equation of motion with the addition of this F mode contribution. And as discussed earlier, this dynamical tide can actually cause the system to evolve chaotically. And this is the earliest study is by Martling in 1995, and there are also later studies of it. And here I'm not going into too much details into it, but I'm just going to use the method by Ivanov in 2004, which estimates the region of the parameter space in which this dynamical tide can drive the system into chaotic motion. So here I'm showing the parameter space formed from the pericenter separation, RP, in a unit of Roche filling distance, such that the system still remains detached. And the x-axis is the eccentricity of the orbit. So in this approximation, we can see for different masses, for system with different masses, we can have different boundary for the transition for the system to go from periodic motion into chaotic motion. And here I'm using a integration of the orbital equation of motion at this particular point to show that a system with this initial parameter will have a chaotic system, which the orbital frequency basically changes over time with a increasing number of pericenter passages. So in the following, we mainly focus on the periodic regime, and actually within our method, we basically assume our orbit to perform a periodic motion in order to simplify our calculations. So now we assume that the orbit itself is periodic, and in order to solve for the equation of motion for the tide, we assume a Fourier series solution of the tidal excitation amplitude, which resembles the solution of a simple harmonic oscillator. So basically, it depends on an amplitude term that is in the form of a Lorentzian, which we call as the mode amplitude factor, and basically is represented as a Fourier series of a sum of harmonics. So in this expression, we can see that if the orbital motion is slow compared to the frequency of the F mode, that is the orbital frequency is much smaller than omega alpha, then we can take the leading order expansion, and this expression basically reduces back to 1, which gives us the result of an equilibrium tide. And if we subtract this 1 of the full expression, then we'll have the so-called dynamical tide effect of the tidal interaction. So from that, we can obtain an expression for the precession. So basically, we write it in terms of a sum of harmonics with this mode amplitude factor given in the previous slide, and also a overlap integral that is given for F mode. And it also depends on some function of eccentricity and some power of the orbital separation. And as an example, I'm showing one orbit with equal mass 0.6 solar mass and eccentricity of 0.5 for the precession rate of the system as a function of orbital period. And I'm showing both the contribution from dynamical tide and the rest of the effect, including the equilibrium tide and the first post-Newtonian effect. As we can see, in this dynamical tide contribution, there are multiple crossings of the resonance in which the higher harmonic basically goes near the F mode frequency at this region. And other than that, the off-resonance part of the dynamical tide basically has a smaller contribution than the equilibrium tide and the 1 TN correction. And if we look at the off-resonance part, we can see that this off-resonance part basically goes as 1/8 to the 8th power, in contrast to the equilibrium tide, which means it is much steeper. So we want to know how much this off-resonance tide can cause the effect to deviate, because the resonance effect is so narrow here. So we first want to look at the off-resonance part. To do that, we take the approximation of our mode amplitude factor to the leading order, which ignores the effect of resonance. And we want to maximize the previous formula for the precession by choosing a certain set of parameters. First, for the separation, we want it to be at Roche loop filling. And for the eccentricity, we set it to 0, such that the system is always at its closest distance. And for the mass ratio, we set it to 1, as shown on the plot on the right-hand side. When the system is at equal mass, both the equilibrium tide and dynamical tide takes the maximum value. And what we find is that this dynamical tide can have potential to give a 25% of difference compared to the equilibrium tide, which means if we have ignored this defect in the parameter estimation, then this is going to cause quite a significant systematic error in the analysis.
Julian, 3 more minutes.
Okay, thanks. So now we want to look at the resonance part of the tide. So basically, we can see from the previous plot that this resonance peak are kind of narrow, but they increases, the width of resonance basically increases when the system goes closer to each other. So we look at the width over space ratio, which is defined by delta FR by delta FS. Basically, delta FR is the region in the frequency space which the dynamical tide contribution from a single mode exceeds that of the equilibrium tide. And for the delta S here, it's basically the spacing between each subsequent resonance. So as we can see from the plot on the right-hand side, if we plot this ratio for systems with different eccentricities as a function of the orbital frequency, we can see that this ratio basically increases with the orbital frequency as we expect. And for systems with higher eccentricity, this ratio also increases because this spacing between each subsequent resonance basically decreases when we have higher eccentricity. And one thing that we have ignored in this analysis is that we have set the system to be periodic, kind of artificially. So if we look back into the chaotic boundary plot, you can see that some of the systems here shown here are basically within the chaotic regime. So basically, some of the systems will have a completely different waveform from the others that are periodic and precessing. So here, I'm going to give a summary of the results here. So basically, what we find is that the dynamical tide becomes more important when the system is at close separations. In particular, for the systems we've considered here, that is the equal mass 0.6 solar mass systems, this dynamical tide start to become important when the orbital period is less than 10 minutes. And for the specific details, we look at the off-resonance piece of the dynamical tide and find that it has potential to contribute up to 25% of the overall precession. And this effect kind of increases for system with smaller eccentricities. On the other hand, for the resonance response, we find that it takes up to around 10% of the frequency space when the system is at close separation. And this effect increases when the system has larger eccentricity. And lastly, we also show that for certain systems with high eccentricity and small separation, it basically transits into a chaotic system, and this completely alters the waveform. So lastly, I'm here just showing one example of the chaotic waveform within the circuit region I showed earlier. And we can see that the frequency domain chaotic waveform basically has a non-zero frequency power, non-zero power at any frequency in between each harmonics, in contrast to a periodic waveform which contains only the equilibrium type. However, this waveform still consists of the same, still have the same shape in terms of the profile inside the frequency domain. So basically, this is the end of my presentation, and I'm happy to take any questions. Thank you.
Thank you very much, Julian. So let's see if there are already questions. I don't see anything in the chat. I see lots of clapping hands in the participant list, but no hands up. Anybody? In the meantime, I can ask a question.
Sure.
How much does the this effect of the dynamical tide depend on the properties of the white dwarf? And how do we know the properties of the white dwarf well enough?
So basically, the properties of the, say, the internal structure, the composition of the white dwarf enters through this overlap integral. So in this formula, we can see that the precession basically goes as the overlap integral to the power of square, to the squared, and and basically we have actually done a plot of, I haven't shown it here, but overlap integral basically has a slow varying function in terms of the mass of the white dwarf. So it is like kind of a constant. So I mean, it has a range of around 0.1 to around 0.2 in terms of the magnitude. So it is more or less a constant. And yeah, this is what I can say about how this precession depends on the composition of the white dwarf itself. Oh, it also enters through the F mode frequency here as well. But if we are looking at the so in this analysis, we have only focused on the fundamental mode, but the composition of the white dwarf also causes other classes of mode, like the gravity modes, G modes, and some sort of that. If we want to measure these quantities, we will need to include also the other classes of mode into our analysis as well, which we have ignored here. So I'm not sure if that answers your question.
Yeah, no, thank you. I think I have a follow-up question, but let me first see if there are other questions. I don't see any hands. I don't see anything in the chat. And so the follow-up is basically, indeed, do we know this well enough? And the background is that I know from the work I've been involved in these interacting binaries that it's not so obvious whether the accreting white dwarf will be tidally locked in the orbit, yes or no, because the viscosity of the white dwarf is so poorly known. And so my question was, this uncertainty, does it impact your work?
Oh, yeah, sure. And it's actually something we are still looking at right now. So, so near the resonance, depending on the viscosity of the system can actually be locked at near the resonance. And this is something we really want to know right now, whether it is possible for this higher harmonics to be locked within the F mode frequency. but currently we still don't have any result for that. So yeah, this is still an unknown for us.
All right, thank you. We may have gone a bit too technical for some of the audience. Let me see. Final call for questions. If not, let's thank all the speakers of this session again.
Thank you.
And so this brings us to the end of the first part of the Astrophysics with Lisa second parallel session. We now have a short break. Apologies, kids are playing outside, so you may hear some shouting. But we reconvene again 15 minutes from now with another 4 very interesting questions. Thank you all and see you back in 15 minutes.
Well, Jordi, are you there just now to test your screen share?
Hi, yes, I am.
Hi, perfect. If you want to try that now, that should work.
Yeah, let's try that. So is this visible?
Sorry, could you say that again?
Is it visible? It's on now.
Yes, that's visible.
Perfect.
There's a bar
Perfect.
across the bottom for the movie, but it's still visible.
I think that was my cursor probably.
Ah, fine. Perfect.
Yeah. Good. Great. Thanks.
Brilliant. Thank you. Hi, Matthew. Do you want to test your screen share as well just now?
Hi, yeah, I'll test it now.
Perfect.
All looking good?
Yes, that's. I can see your whole browser, but do you want to
Yeah.
test presentation mode? Yes, that works.
Cool, thanks.
Thank you.
All right, we're almost ready to go. I think we're still missing one of the speakers, right?
Yes, I haven't heard from who is he second? Yes, Shobit was second. So I am thinking that we should move Mesut and Jordi up by 20 minutes each.
Yeah, let's do that.
And if he joins, he can take the fourth slot.
That's correct. I
If
agree
that's
with
okay with everyone. Okay.
Mesut, is it correct? Is that okay for you too?
Yes, it's also okay with me.
Ah, there he is, or she.
Nice.
I think we have Shobit now here. So maybe
Hi,
we can keep
Shobit.
the original
Yes.
schedule then.
Yes, hi. Can I test my screen share as well?
Hi,
Yes.
yes, of course you can. Go for it just now.
Is it looking fine?
Yep, that looks perfect.
Okay, thank you.
All right.
We'll maybe just leave 1 more minute for the break for everyone to come back, and then we can start back up again.
Let me use that time then to repeat or say to the speakers, I'll give you a warning after 12 minutes. When I'll say you have 3 more minutes, then I'll give you another warning after 14 minutes saying you have 1 more minute. And then I really hope that you wrap up within 1 minute so that we have some time for questions because we cannot afford to run over. All right. Ready to go, Rona, you think?
Yes, on we go. Thank you.
All right, so welcome back to session 2 out of 2 of Astrophysics with Lisa. 4 more speakers. I'll just introduce them along the way. Our first speaker is Matthew Mould from the University of Birmingham, and his talk is about enhancing gravitational wave population inference with deep learning. Please share your screen and go ahead.
Cool, okay, thanks. Hi everyone, hope you're all doing well. Thanks for having me. I'm Matt, I'm a PhD student at the University of Birmingham. Yeah, and as has just been said, I want to talk about some work we've done applying deep learning approaches to the population problem for ground-based sources. So far we've detected mergers across a range of source types, but I'll be focusing on stellar mass black holes. And we've detected sources across a range of masses from a few solar masses, a few tens of solar masses, up to merger remnants, which are pushing into what you might call the intermediate mass regime. above 100 solar masses up to about 150 solar masses, let's say. And so the question now is, how do we form such sources? Because in the traditional kind of picture of isolated binary evolution, these heavy black holes are hard to form. And the way we're going to study now catalogs of detections made by LIGO Virgo is to do a Bayesian inference. And one of the ingredients in any kind of Bayesian analysis is a prior. So a prior model for what we think the distribution of these sources looks like. And the most common approach that has been taken so far is to use parametric models. So you kind of come up with some mathematical form that you think correctly describes the distribution of the properties of our binary mergers. So things like masses and spins. But this isn't so great in that it's not really astrophysically motivated. It's just kind of something we come up with off the top of our heads. A different approach is to take a simulation-based approach. So if you have some kind of forward model which produces a set of binary mergers, so for example, a population synthesis simulation, now we can fold in kind of all of the astrophysical realism which is feasible into our simulation, and compare this against the detections we make. The only problem is we want our prior to be continuous over the parameter space, whereas if we have kind of discrete simulations, we don't have that continuity. We only have a finite set of simulations. But what we can do is employ some interpolation or emulation techniques, and this is where deep learning is going to slot into our Bayesian pipeline. So now I'll just describe kind of the simplified set of simulations we perform, which aim to kind of describe the production of the heavier end of black holes we see with LIGO Virgo detections. So we set up kind of simple numerical simulations in which we start with a cluster of black holes, and cluster really is not really an astrophysical cluster, just kind of a collection of black holes which can potentially pair up and merge. And we have some kind of parameters which describe the initial masses and spins of that cluster of black holes, as well as an escape speed, which is kind of a crucial parameter for these clusters. And then we have some other parameters which kind of characterize the probability of pairing two black holes into a binary. So one by one, we draw black holes from these clusters, we pair them into a binary, and then we estimate the merger remnant properties using numerical relativity fitting formula. And one of the parameters you estimate is the magnitude of the recoil kick received by that merger remnant. Now, if that recoil velocity exceeds the escape speed of the cluster from which the binary came, it's ejected and it isn't placed back into the cluster. So it can't, the merger remnant can't then go on to pair up into a new binary. If on the other hand, the kick velocity is smaller, then we place that remnant black hole back into the cluster, and it can go on to pair again into a new binary and merge. And so this is what we call the hierarchical or repeated merger scenario, where merger remnants can then go on to form subsequent binaries and merge again. So your typical scenario is listed here, where we have two what we call first generation black holes, which are born from stellar collapse, let's say. And then second generation black holes, which have already undergone one merger and then may either merge with a first generation black hole or another second generation black hole, or there might even be high generations where multiple mergers have happened. And so these simulations result in distribution of the binary source parameters that we see in these four panels. So we model the chirp mass, the mass ratio, and two effective spin parameters. Chi-F is the usual effective aligned spin, and Chi-P is an effective parameter which characterizes the spin precession of a binary. And with our definition, this consistently incorporates both black hole spins. And so this parameter is now defined between 0 and 2, with sources above the Chi-P equals 1 line being signatures of that there's two precessing spins in that system. Okay, so we do many simulations, and we we construct a discrete bank of binary distributions this way. Now we want to interpolate it so we have a continuous model rather than a discrete set of simulations. And so we use deep learning to do this. For each of 1,000 simulations that we perform, we first construct a density estimate over the joint 4-dimensional space of these 4 source parameters with a KDE. And then we interpolate across the space of this prior density, which is a joint space over both the source parameters and the population level parameters, which we're going to constrain with our hierarchical inference. And we emulate this function with a deep neural network. And this consists of 5 hidden layers with 128 nodes in each layer, and some output which enforces our probability density to be positive. And I'll also point out this work by Case Wong, which takes a similar approach to performing this kind of deep learning based population emulation. For each of the mergers in our simulations, we also estimate the probability that we would detect them with our ground-based interferometers. And this can be used to construct what's called the detection efficiency, or the selection function, which is just the fraction of sources from a population you would expect to detect. And this is going to be very important because the mergers we see with our detectors aren't fair draws from the population. They're filtered through the biases imposed by our detectors. And so we need to account for that in the hierarchical inference. And so we also construct a deep neural network which interpolates this selection function across the population parameter space. And a final network we construct, which doesn't enter the hierarchical inference, but is useful in post-processing, is a neural network which predicts the branching fractions between the different merger generations I described. So what's the fraction of sources which are 2 first-generation binaries? What are the fraction of sources where we have this mixed first and second generation, or 2 second-generation sources? And then the remainder of sources which have undergone potentially multiple mergers. And again, we can construct a deep neural network which interpolates this function across the population parameter space. And so all of these ingredients get combined into our population level likelihood. So unlike your kind of usual parameter estimation, where you want to make inferences on individual sources, where we want to find out what are their masses and spins and redshift and sky position, etc. In the population likelihood, we want to combine all of the detections we've already seen and which have already had, their parameter estimation done for them. We define a new likelihood which combines all of those events, and as I said, we weight by this detection probability to account for our selection biases. And then we sample this likelihood surface with traditional nested sampling techniques, which many of you are probably familiar with. And so this is the result of that inference. These are the 6 population parameters which enter our model and which I haven't described. But essentially, these parameters are the inputs of whatever your astrophysical simulations are. So if you're doing population synthesis, for example, these are the inputs to your population synthesis pipeline. So you can kind of replace the 6 parameters we have here with anything which enters some kind of population simulation. What's more interesting for us as astrophysicists is not necessarily the distribution of these hyperparameters, but they could in principle. So for example, you see one of the parameters in our model is a maximum mass in the 5th column here. And this is to model some cutoff due to pair instability supernova. So these parameters can be themselves of astrophysical inference, can be themselves of astrophysical interest, but just the way our kind of simplified model of repeated mergers is set up, these are potentially less interesting. But maybe what we're more interested in as gravitational wave astrophysicists is the distribution, the population distribution of the binary source parameters themselves. So as opposed to here where we have a distribution of parameters, now we're looking kind of at a distribution of distributions. So if we take our inference on the hyperparameters and we fold in these Bayesian measurements which are uncertain, we can then go back and look at our population prior, which depends on those uncertain hyperparameters, and construct what do these distributions over the source parameters, so the masses and spins, look like. And this is where we make plots like this. So the panel on the left, I'm showing the distribution of all of the masses implied by our inference on the current catalog of stellar mass binary black holes. And because we split our population into a first generation of sources which form from stellar collapse and another population of sources which form through this repeated merger scenario, we can look at the difference between those two distributions. And what we find, as I said before, is this cutoff in the mass distribution, which is around 40 solar masses, which is kind of broadly consistent with predictions from supernova theory. But there's this extended spectrum of masses due to the heavy black holes we've seen so far with LIGO Virgo. And in our model, those are explained by this repeated merger scenario. And I'll
Matt, 3 more minutes.
Thank you. I'll explore that a little bit more shortly. And then we also look at the spin distribution. So for example, here I've just shown there's the distribution of our processing spin parameter, which kind of features multiple peaks and some minor modes, which in our model, again, is explained by this repeated merger scenario. And because we're modeling the joint 4-dimensional space, these aren't a product of independent distributions, it's the joint 4-dimensional space. We can look at how our parameters are correlated with each other. So for example, here I'm looking at how does our processing spin parameter vary with the primary mass, and how does it vary with the mass ratio? And so these kind of correlated features, which normally we don't model with parametric models, are intrinsically and easily captured by this kind of deep learning emulation pipeline. We can also model things which are inherent to the astrophysical environment hosting the black holes themselves. So in the left panel here, I'm showing what are the distribution of escape speeds of these clusters hosting black holes implied by our inference. And what we find is that though there's a preference for small values implied by this blue distribution, if we also look at the distribution of kicks received by first generation sources, what we see is that many of these kicks are smaller than the escape speed of the host environment. So around 40% of first generation sources receive kicks less than the host escape speed, which means they will be retained post-merger and can undergo repeated mergers. And then the final plot I'll show is this kind of post-processing. Once I have my hyperposterior, I can feed that into this neural network I constructed to predict the branching fraction between different merger generations and get a posterior on those merger generations. And in short, what we find that in our model, about 25% of sources aren't first generation. So at least one of the components has undergone a previous merger. And so that leaves me with my summary. So what I've shown is that we can efficiently emulate kind of simulated merger populations with deep learning techniques. And in the model I present here, the features that we see in the current catalog of stellar mass mergers, stellar mass binary black hole mergers, can be explained by this hierarchical merger scenario. And we employ kind of simple numerical simulations, but this whole pipeline readily applies to any simulation scenario you can think of. And so I've listed a few ideas for the future that I want to explore, but we can also explore applying these techniques not just to ground-based, to populations which are interesting for ground-based detectors, but also for the future space-based detectors like LISA. So thanks for listening.
Thank you very much. Also for keeping to the time perfectly. Lots of applause. Let me see. Oh, maybe I should have repeated. Please ask your questions either typing in the chat or raise your hand with the raise hand button of Zoom. If you're on YouTube, you can type your question there in the chat. This will be monitored. So with all these options, surely there will be questions. If not, I'll take the opportunity to ask one. This is a little bit far from my expertise, but I was a bit surprised about I think you said that these correlations that you could explore with this method, you couldn't do with parameterized models, but surely you can make a multi-dimensional parameterized model where you would get this too, right? Or
yeah, sure. So you can define some parametric model, and people have done this to explore parameter correlation. So you might have seen in the LIGO-Virgo papers the discovery of some correlation between mass ratio and the effect of aligned spin. But you still have to impose some parametric form. So you say, oh, how does the mass ratio vary as a function of chi-f or vice versa? But you have to impose some kind of strict parametric form. Here, the correlations are whatever is implied by your simulations. So you don't have to make any kind of parametric imposition here. So I think the kind of parametric correlations are useful to discover correlations, but they're not so useful to describe why they are there.
Okay, thanks. I think in general, indeed, the fewer parametric models there are, the better, but it's not always easy.
Yeah.
Let me see. Anybody else who wants to ask a question? If not, let's thank Matt again. And let me remind you that via email or the Oxford Abstracts badges, you can still get back to Matt if you discover you have a question later.
Thank you.
All right. Thank you very much. We move to the second talk of the session by Shobit Ranjan on multi-band gravitational wave astronomy, measuring recoil kicks. Shobit, please go ahead.
I'll just share my screen.
Share your screen.
I hope it's visible.
Yes, and we can see you.
Okay.
And we
Alright,
can hear you.
so-
All right, go ahead.
All right. Well, hello everyone. I am Shobit Ranjan and I am presenting my results on measuring recoil kicks with LISA and ground-based gravitational detectors. I recently graduated with a bachelor's from Delhi Technological University in India. This work I did at Vanderbilt University under the supervision of Professor Karanjani and Professor Kelly Holly Buckelman, in collaboration with Dr. Alex Neitz at AEI and Kurt Cutler at JPL. Coming to recoil kicks are primarily a result of anisotropic emission of gravitational waves from a binary black hole merger. These gravitational waves actually carry away angular momentum and energy, but they also carry away linear momentum, resulting in a kicked remnant black hole. The magnitude of kick is generally higher for precessing systems, and furthermore, the kick depends on 6 individual spin components and mass ratio of the binary. On right, you can see an animation from the GW surrogate model I have been using in this study. So after merger, after ring down, the final remnant black hole is kicked out from the center of mass of the system. So the projection of spins has been measured fairly well with the LIGO-Virgo observations, as well as individual masses and mass ratios, but a reliable measurement of recoil kick is something that has remained elusive. LIGO-Virgo collaboration did report the kick measurement in the GW 190521 paper, but the constraint was very poor. There are, of course, astrophysical implications of constraining recoil kicks. Some fine-tuned spin configurations can reach super kick values that is enough to escape out of clusters or galaxies. So, of course, naturally, the growth of black holes is associated with the magnitude of kicks, and this also has implications for galaxy evolution. We are trying to answer the question if we can constrain the recoil kick magnitude with multiband measurements in LISA and ground-based detectors. So this is a plot of 2 merging binaries. This particular case is for a binary resulting in a 150 solar mass black hole. Both binaries have same intrinsic parameters. That is, they have the same masses, same spin magnitudes, same projection of spins. The only thing that differ in is the azimuthal orientation of spins, or you can say the direction in which the individual black holes are spinning. These binaries will be visible in LISA starting at 10 millihertz, which is years before they are visible at a higher frequency in ground-based detectors. Both these binaries, although very similar at the beginning, have very different fates after merger. For example, one of the binaries ejected out of the system with a moderate kick of around 60 kilometers per second, while the other one is shot out at about 1,000 kilometers per second. So moving on to the method we have employed, we first start with the signal in LISA, many years before it comes down to the ground-based detectors. From this observation, we infer what we can about intrinsic parameters such as the spins and individual masses. We then use this constraint while constructing the parameter space for running Bayesian inference on ground-based detectors. So in a way, we are shrinking down the prior for ground-based detectors to be aware of the region where LISA says that this particular parameter of spin or the mass ratio lies. So here are some characteristics of our analysis. So we start with LISA, where the low frequency we start with is 10 millihertz. We're employing a Fisher matrix analysis pipeline on LISA. And we are also using the IMR Phenom XPHM model for LISA. And then we're getting constraints on spins and masses. When we move on to ground-based detectors, we have an f-start that varies with detectors. So for example, current generation detectors, Virgo, LIGO at design sensitivities are anywhere around 10 to 12 hertz they start. And third generation detectors like Einstein telescope starts anywhere from 3 to 5 hertz. This inference is now, ground-based inference is now aware of what LISA has observed. Again, in a way, we are shrinking the prior space to size as LISA given us. And we obtain the posterior of the 6 spin components from here. Finally, we move on to the remnant analysis, for which we are using the SurfinBH pipeline, which uses a combination of numerical relativity surrogate 7DQ4 model and another surrogate 7DQ4 remnant, where the remnant model is trained specifically for analyzing merger remnants using GPR on numerical relativity simulations. Getting to our results, so we start first with looking at the recovery in the best case scenario with current generation detectors. Spelled out here as HLVIK, that is Hanford, Livingston, Virgo, India, and Kagra. We see that they have a hard time distinguishing between the low recoil kick magnitude and the high recoil kick magnitude. The left one showing the low recoil kick of around 70 kilometers per second, and the right one showing it at about 1,000 kilometers per second. Basically, it's particularly blind to distinguishing between these two kick magnitudes. So LISA alone does a pretty good job of constraining one of the kicks, but not the other. And so the left one, you can see that it is doing a very good job at constraining the 70 kilometers per second kick, but is very uninformative of the higher kick magnitude. Now moving on to Einstein telescope alone, we see that it does a pretty good job on constraining both low and high recoil kicks. Not only is it able to distinguish between the two, it is giving us a very reasonable posterior to work with. Moving on to the multiband. So here we are multibanding Einstein telescope with LISA. Again, so we are running the analysis in Fisher analysis in LISA. We are getting the constraints on spins, 6 individual spins, mass ratio, putting that into the prior of Einstein telescope, and then running the Bayesian inference all over again to obtain this particular plot. So you can see that this is particularly the best case scenario we have. Again, not only does it manage to distinguish the two cases, we get extremely good posteriors to work with. We also saw that this is an improvement over using ET alone, the Einstein telescope alone, or using LISA alone. The problem with using just LISA is that it does not manage to constrain the parameter for all cases. So we saw that it did a pretty good job for the low kick case, but it is blind to the magnitude of high kick case. It's pretty much similar to what we get from the HLVIK network. So this table also supports the conclusions that HLVIK is blind to the injected kick magnitude. With an extremely broad credible interval, LISA does fairly well for the lower kick magnitude, but fails to do the same for the higher kick case. We also observed the fact that LISA isn't performing similarly across the two cases, of course. And Einstein telescope is able to distinguish between the two cases and give us a fairly narrow credible region. But Einstein telescope working with LISA is in a league of its own. For both cases, the median manages to be fairly close to the injected value, as well as the credible regions, which are very narrow. This is the most accurate measurement of kick we can hope to do. Moving on to our conclusions. So working with two cases of kick, we concluded that the current ground-based network, even at its advanced plus design sensitivity, is largely agnostic to kick measurements, even at its best advanced plus design sensitivity. Third generation working alone shows much more promise for measuring recoil kick, but multibanding the system with LISA takes the trophy. So it is giving us the most accurate measurement of recoil kick. Since kick is just dependent on 6 spins and masses, it remains blind to all extrinsic parameters. We also studied the direction of recoil kick velocity, recovering the full velocity vector of the remnant. So not just the magnitude, but the direction as well. So we obtain constraints on kick magnitude, which of course can be used for further astrophysical analysis, placing the constraints on rate of detention in black hole binaries as well. Thank you so much.
Thank you very much for your talk. It was quite short, but that's good. We have plenty of time for discussion. And let's see if I do see a hand. So let's go ahead, Matt.
Hi, Shobit. Thanks for the talk. I wanted to ask, so why are the different detectors better for lower or higher kicks? Is there something intrinsic about high and low kicks, or is it to do with the binary parameters which produce those kicks?
Okay, so to answer that question, I'll first go back to this particular plot. So first, like the only difference between these two cases we are using is the azimuthal orientation of spins. So LISA doing better for one and doing worse for the other is, I think, only depending upon what the azimuthal orientation of spin was. So it was favorable for the antenna pattern of LISA while working with Fisher analysis. So that is one reason why it might be able to observe it better. So it's a very sweet spot case. It wouldn't apply to all spin orientations. So that is one way of showing that, you know, LISA will only do it like it will be a roll of dice with LISA alone. But while working with others, we can be sure that, you know, we'll get a pretty good posterior for recoil kick measurements, because LISA is also putting constraint, and then independent antenna patterns across multiple detectors wouldn't depend on what kind of spin orientation we have. I hope that was able to answer your question.
Yeah, thank you.
Thank you.
Thank you. Any other questions? There's a comment in the chat that there's more degeneracy for low kicks versus high kicks. That's one of your supervisors, I think, right?
Right, yes.
So,
yeah, this is quickly, I just wanted to add. So there are more things that make low kicking black holes than high kicking black holes. And so the number of configurations, end up making the error bars bigger, for even if it's the same detector sometimes.
Thank you. Don't see any other. So there's a question in the chat. Have you analyzed the SIGO's ability to determine kicks? I ask as it spans the gap between ground-based and other space-based interferometers. Are you aware
Can you repeat that?
So the question is, have you looked at the detector with the sensitivity in between LISA and ET? And so one of them is a concept from Japan, the SIGO.
Yes, so I haven't actually looked at that. That will surely be something in my future works. But of course, like that is a huge part of multi-banding with detectors in different frequency bands. So that will be something I'll be working on in the future for sure.
Thank you. I don't see any more questions, so let's thank Shobit again.
Thank you.
And we move to the third talk in our session by Masoud Khan from Johns Hopkins University on observability of lensing of gravitational waves from massive black hole binaries with LISA. And please, we see your slides.
Hello, everyone. Can you hear me?
Yes, go ahead.
Okay. Hello, my name is Masoud Khan. I'm a first-year graduate student at Johns Hopkins, working with Mark Kamionkowski and Emanuela Berti. I am going to discuss observability of lensing of gravitational waves from massive black hole binaries with LISA. So, as you know, the lensing of electromagnetic waves have been widely used in studies of astronomy, astrophysics, and cosmology, including in concerning the dark matter, measuring the Hubble constant, and many more studies. Now, similar to electromagnetic waves, gravitational waves can also get lensed. Now, while the principles for both phenomena are the same, there are some intriguing differences. There is the lensing of electromagnetic waves is usually treated under the geometric optics approximation, where the wavelength of the emission is much smaller than the physical size of the lens. While this may be generally true for lensing of light, that is not necessarily correct for gravitational waves. That is, if the wavelength of the emission is similar to the size of the lens, then we need to consider the wave optics effects to get a full picture of the lensing that is going on. That is, if the lens mass follows this condition that you can see here, then we need to consider the wave optics effects. Here, F is the frequency of emission of the gravitational waves, and ML is the lens mass. For an axially symmetric lens, lens mass is defined as the amount of mass that is enclosed within the Einstein radius of the lens. So it may not be necessarily the same as the total mass of the lens, but it's the mass inside the Einstein, right? So if this condition is true, then we need to consider the wave optics effects. To get the effect of lensing on gravitational wave propagation, including all these effects, we need to solve the complex value diffraction integral F, which is a function of frequency, as you can see here. So here, the capital D's are the angular diameter distances that you can see from here. The psi naught is usually the relevant scale of the problem. It's a normalization factor, which we use to choose to be the Einstein radius. Here, this integral is over all possible paths, including those that are not geodesics. The two vectors x and y that you can see here depend on the physical coordinates of the image on the lens plane, as you can see here, or the source on the source plane. Y is named the impact parameter, and it's a very important parameter in question, so please keep that in mind. TD is the time delay for a given path. So if you want to get the lens gravitational waveform in the frequency domain, you need to know that the lens gravitational waveform is the product of the unlensed waveform and the diffraction integral F. Now we look at the spherically symmetric lenses for discussion here, which then we can write it as a function of W and Y. Y is the impact parameter and W is the dimensionless frequency, which I define here. Now, luckily for us, for point mass lenses, we have an analytical solution for a long amount of time, which depends on the gamma function and the confluent hypergeometric function as a function of W and Y. For simplicity, here I write the dimensionless frequency W as a function of the redshifted lens mass MLZ and the frequency F. So for a fixed lens mass, W is a function of the gravitational wave frequency F. So we have a solution for the point mass lens. So for the singular isothermal sphere lenses, this is the form of the diffraction integral F as a function of W and Y as before. The issue is that both the exponential and also the Bessel function in the integrand can oscillate rapidly, which means that the numerical evaluation of this integral is tricky. Now, while there are several numerical approaches that have been proposed in literature, they may be costly. Therefore, they prevent us from using them in a grand scale study. Here, we propose and implement an effective method that gives us an analytical solution to this integral that is based on the Taylor expansion of the exponential factor that you can see here. Then we define the important integral In of W and Y, which luckily has an analytical solution that depends on the gamma function and the confluent hypergeometric function, then we define the exponential factor there, the expansion. And then once we have these two things, then we can get the diffraction integral for the SIS lens in this form. But in the next slides, I show you the amplitude and the phase, the argument of the diffraction integral obtained for point mass lenses on the left-hand side and SIS lenses on the right-hand side as a function of dimensionless frequency W for varying impact parameter values that you can see here. So on the left side, this frequency-dependent effects that you see are diffraction effects. These are the wave optics effects. As you can see, for both amplitude and there's the amplification factor and phase, they depend on the frequency. As we increase the W, we get into this region where modulations are very high. Here is the interference regime. It's because gravitational waves are coherent and we have multiple images in this regime. And because they're coherent, they interfere with each other if the time delay caused by lensing is shorter than the duration of light, which is true for some cases with LISA. So using our analytical solutions, we can calculate the diffraction integrals for the both cases. Now let's look at the lens gravitational waves and the information matrix formalism to understand how this affects the lens gravitational wave and what we can learn from these effects. So here you see the amplitude as a function of frequency of the reduced time delay interferometry observables AET of LISA. This is because of the orbital motion of LISA around in its orbit around the sun. You see the inspiral, merger, and the ring down. So now this is an unlensed waveform. Now we ask the question, what if this is lensed by, first of all, point mass lens? Here we get a reference lens with 2 × 10⁷ solar masses in lens mass, and we fix the impact parameter to 1. And this is how the lensed TDI observables look in amplitude as a function of frequency. Now, if we keep everything the same, but change the lens model to the singular isothermal sphere model, this is how it looks. So the observable that you see depends on the lens mass, the impact parameter, but also the lens model that you have, and depending on that, your observable changes. Now, to perform parameter estimation, especially to get the observability of the lens parameters, we actually form our information matrices that include all the 11 source parameters that I list for you here, including 2 aligned spin parameters, as well as the 2 lens parameters, that is the redshifted lens mass and the impact parameter. Overall, our variance covariance matrices are 13 by 13 in dimensionality. For the waveform models, we use the phenomenological gravitational waveform model such as IMR phenom D for the quadrupole only case. And if you want to include the higher order modes and look at their effects, we use IMR phenom HM waveform model. The reason that we can get this is because we have analytical solutions to the diffraction integral, therefore we can get the derivatives as well. So now that we have the information matrix formalism under our belt, let's continue. So let's look at the effect of merger, ring down, and the higher order modes. So here I'm showing you the measurability of relative uncertainty of the redshifted lens mass as a function of lens mass for a point mass lens that is fixed and an impact parameter 0.1 that is fixed. And here we have a reference binary with total mass about 2 × 10⁶ solar masses, mass ratio 1, and we place it at redshift 1. Now we fix the spins to be 0 for this initial case, but we randomize all the other parameters hundreds of times. And here the high opacity line shows you the median value that we get. And the low opacity line shows us the 68% confidence interval. So here you can see the measurement uncertainty of the lens mass. And ISCO stands for here that the waveform here is the inspiral only waveform. This is the waveform that has been used in the literature before. So this result is what we have in the literature before. And this is our result, but our result matches the result in literature. But now the question is, okay, we can measure the lens mass, but what happens if we include the merger and ring down to the signal? Because this hasn't been studied before. So once we include the merger and ring down and repeat the same exercise, what we find is that adding the merger and ring down actually decreases the measurement uncertainties by almost an order of magnitude. And as a result, the lowest lens mass that we can measure also decreases by an order of magnitude. As opposed to 10⁵ in the previous case, now we go to the 5 × 10⁵. And even if you think that 100% relative uncertainty is too high, like too bad for a threshold, if you put it at 10% relative uncertainty, it changes from 10⁶ to about 5 × 10⁴. Now the question is, what happens if our waveforms also add the higher order modes? then this is what happens. And this is a conservative choice, and a binary with mass ratio higher than 1 would here show a more drastic improvement thanks to the higher order modes. Before we move on, what we see here is that as we increase the lens mass, now we have more lensing going on, and we have frequency-dependent effects that enable us to measure the lens parameters. As we increase the lens mass, the errors decrease. At some point, we start to leave the wave optics part and hit a dip in the diffraction integral. This is where the errors increase again, but then they decrease again because we now are in the interference regime where the double images interfere with each other, and so we can measure the lens properties once again. Now, this is only for the lens mass. When we repeat this exercise for the impact parameter, we also see the similar improvements thanks to the merger and ring down. Now, if you repeat this exercise for different impact parameters, different binaries, and also for the SIS profile, the single isothermal field profile, we see the same results. I'm just showing this one as an example. Now that we understand the effect of merger and ring down and know that using in-spiral-only waveforms underestimates the measurability of lensing, I am moving to the effect of the source parameters. Here, for a reference binary, we fix every parameter, including lens parameters, except the inclination angle in this case, and we randomly sampled about 100 times. And with the colors here, in each beige is one realization. And with blue and green, you can see the face-on and edge-on binaries. On the right-hand side, this is how the inclination affects the measurement uncertainty. It's about 20% variability due to the inclination angle. On the left-hand side, I show you the normalized to SNR results. Here, we normalize the measurement uncertainty to the unlensed SNR to see whether a source parameter makes an effect due to a change in the SNR or something more intrinsic. And by looking here, we see that inclination angle makes an effect, not only due to a change in the SNR, but allowing us to probably break the degeneracies by making the higher order modes more prominent. Now, when we ask the same question,
three more minutes.
All right, thank you. For component spins, we see that they make a 50% effect, and also in the normalized SNR case, they also make an effect. Now that we have this understanding, we do look at the measurement of the lens mass and the impact parameter in a wide range of the lens parameter space. On the horizontal line, you have the redshifted lens mass, and on the vertical line, you have the impact parameter. For a select binary, the colorful areas is where we can measure the lens parameters. As you can see, the lens parameters are measurable thanks to the wave optics effects in a wide region of the parameter space. And because of the merger and ring down, these limits are way higher. Now, if we keep everything the same, but change the lens model to SIS, this is how it looks. Now, there's one important part here, that is the highest measurable impact parameter that we have here is not a constant as it was believed in the literature before, but it's a function of the lens mass. So an accurate study of lensing probability needs to consider a case-by-case basis of a lensing situation with the lens and source population. But overall, what we find is that including the higher order modes, merger and ring downs enable us to measure lens parameters in a wide range of the parameter space. Now we repeat this exercise for other select binaries that you can see here on the left-hand side, measurability of lens mass and impact parameter on the right-hand side for different binaries in each row. In each case, we have a wide range that gives us measurable lensing. To summarize the results, here I show you a table in which you can see the critical impact parameter, highest one that we can measure, or the lowest lens mass that we can measure for different binaries. Now, we also repeat this exercise for the SIS lenses, and again, I show you the final results. Again, what we find is that we can measure lensing up to very high impact parameters and up to lower than previously thought lens masses. Now, let's conclude. So first, what we know is that wave optics effects in the lens gravitational wave signals are vital. They cannot be ignored. Frequency-dependent wave optics effects could lead to a plethora of applications such as precision tests of cosmology. You can use for the time delay cosmography. You can maybe use them to constrain the lens population because they enable us to actually measure the lens parameters directly. Now, this is to our knowledge, the first study that utilizes the analytical solutions and derivatives of the lens and diffraction integral for the SIS lenses. And it's also the first study using gravitational wave models that include the merger, ring down, higher order modes, and aligned spins. I also want to mention that it's also possible to use these wave optics effects to break the mass sheet degeneracy, but which is to be studied. Now, we find that in spiral-only waveforms used in the previous studies overestimate the measurement uncertainties in the lens parameters by about an order of magnitude, and then merged ring down on higher order modes significantly improve our ability to measure the lens parameters. And while we may need to consider, because we can measure really high lens parameters, maybe more than one lens in the line of sight with the impact parameters small enough, maybe we need to consider line of sight halo contributions, and maybe other complexities. We may need to improve our analysis for other lens models such as NFW. But nonetheless, wave optics effects gives us a great powerful tool to learn about the lenses and the sources. And regardless of any of these, a new era of lensing studies is waiting for us, thanks to wave optics effects. Thank you.
Thank you very much. It was well timed. Almost beginning to wonder why I'm chairing this session anyway, because all the talks are on time. Anyway, that's great. Any questions? Either raise your hand or type them in the chat or in the chat of the live stream. Well, there are no questions yet. Let me then ask the first question. So for lay people like me, can you give some indication how this maximum value of Y relates to sort of a probability of lensing?
Oh, very great question. So for the lensing of light, the maximum impact parameter Y value that you can get that information is 1. And lensing probability is proportional to the square of the impact parameter. So even if you cannot measure lensing up to 50, but let's say 10, that means that the lensing probability would be 100 times that of strong lensing. So even if the rates of the massive black hole binaries are low and that we don't expect that many strongly lensed systems, let's say we expect 5 or 6, and I know Alberto Cesana is in the audience today and he had a paper on it about 10 years ago with Sereno. What is important is that by measuring high impact parameters, you actually increase your lensing probability by a lot. That is the square of the impact parameter. That's how it is proportional.
Thank you. So there's a question. Do you expect the lens parameters to be degenerate with mass or spin? How much do we expect the errors to degrade?
Okay, so in our variance covariance matrices, we look at the variance and also covariance between all the mass and spin parameters. So spins, the aligned spins are included. Actually, including these parameters do help. There is some degeneracy when the lens mass and impact is very low or impact parameter is very high. But our study includes 4 possible degeneracies between by including all these parameters. Now, I don't know whether eccentricity, etc., and how they would affect, though they need to be studied. If I understand the question correctly.
I think yes, because
thank you, Marco.
Question: can you elaborate on how this can break the mass sheet degeneracy?
Yes, so I think what happens is that in a portion of the wave optics regime where the lensing is strong enough and interference regime starts, where you have these double images interfering with each other, Cremonese and Jose Maria Esquiaga, Jose is at the University of Chicago, they looked and then they seen that you may have enough information to do parameter estimation, let's say on directly the lens mass, not the redshifted lens mass and the lens redshift. But this is one of the things that I want to try now and see whether we can actually estimate the lens mass. So to what accurately this can be done, we don't know, but we know that in this small regime that I showed you today, you may have enough information in your signal to actually measure these parameters directly instead of measuring the redshifted lens mass or impact parameter. You may look for physical parameters and try to measure them, but we don't know how well they will measure. This is a question of our next study. Thank you, Alexander.
All right, thank you. Don't see any more questions. We still have 2 minutes, so let me ask then my other layman question, which sort of precedes all this. So, but you can recognize that you're dealing with a lensed signal rather than a more distant, more massive one, like we had some discussion with the ground-based detectors.
Yes, well, I think that's one comes from, maybe I can go back a little bit, because if we had let's say in the lensing of light, you have that full degeneracy between the two. Then if you had lensing, your signal would just basically get bumped as a frequency independent way, and your phase will be either the same or be shifted by an integer multiple of pi/4. But when you have this wave optics effects, this is how your signal changes. It changes in both amplitude, which I show here, but also in phase in a frequency dependent fashion. And then you get to see these modulations, which are very different than what you would have if you were completely in the strong lensing regime without these wave optics effects. But now there's a question, can any other thing replicate this, or do you have the correct lens model? These needs to be more carefully thought. And one improvement, for example, would be to do this study not on a, let's say, not on an SIS lens, but NFW lens, or maybe push this further so that we have a template bank for many kinds of lenses, not only these two.
Hey, I can't hear you there.
Yes, I couldn't hear either.
We had that yesterday too. Can you hear me now?
Yes, that's better. Thank you.
All right. So let's thank the speaker again. We move to the last talk of this session by Jordi Davila from Columbia and Flatiron Institute on probing black hole shadows via electromagnetic self-lensing flares. Go ahead, Jordi.
Thank you very much, guys. Yeah, so it's a nice step from gravitational wave lensing to electromagnetic lensing. So this is a project that I worked on together with Zoltan Heyman here at Columbia and the Flatiron Institute. And well, let me first elaborate why we think it's important to look for self-lensing signals from black hole binaries in general. So let's see, why is it? So currently there are around 150 black hole binary candidates, supermassive black hole binary candidates found via large time domain surveys. However, these are typically found by looking for periodicity in their light curves. And this can be degenerate with, for example, just your vanilla AGN accretion variability, which follows a random walk behavior. So one way to lift this degeneracy between a single black hole and a double black hole is to look for events where one of the black holes is actually lensing the background black hole, which amplifies the amount of emission very rapidly and will give a very clear signature in your light curve. So out of these 150 candidates, there's actually one very peculiar candidate who was found in the Kepler data in 2010 already. This candidate is called Spiky, and I show it here on the right side of my slide. So here in black is the Kepler data. And as you can see, it follows some kind of a sawtooth pattern, which is quite typical for orbits who are eccentric. So then the Doppler boosted signal becomes more of a sawtooth-like pattern. And the magnification is plotted here as a function of time. And the moment that you expect the two black holes to line up along the line of sight, there is this massive increase of emission that is observed by Kepler. So one of the ways that people explain this is that indeed the two black holes are in front of each other. The foreground black hole acts like a lens and enhances the emission that we observe. However, this type of effects are typically studied with microlensing approximations, which is a nice way of doing this because it's a simple analytical formula that you can just easily apply on some like point source style source model, and then you can easily go over a large set of parameters. However, we can expect that like the source morphology, the morphology of the emission region is also affected by like GR effects. So the way the black hole looks like, we need to take into account also GR. So why is this important for example, LISA? Well, if we know how these self-lensing flares look like, we can use, for example, ground-based facilities to look for these features so that we can improve sky localization by looking for these spikes. And if we actually measure such a self-lensing flare together with a gravitational wave signal, we can even match the phase of the electromagnetic signal with the gravitational wave signal, which could, for example, allow for graviton mass estimates, as it was explained in the paper by Heyman 2017. So that brings me to the motivation of this study. So our goal is to study these self-lensing flares with general relativistic ray tracing. So general relativistic ray tracing is a methodology where we have some virtual camera somewhere out of our domain of interest, and this camera has a variety of pixels. Every pixel is assigned a wave vector, which we then use to solve the geodesic equation. So the geodesics that we obtain can then be used to solve the radiation transport equation, and therefore we know how much emission arrives on the camera for every single one of these pixels. So for our study, we used the ray tracing code that I developed during my PhD program in the Netherlands, which is called Raptor. So the physical model that we used is here shown on the right as a nice cartoon. So the binary is on a Keplerian orbit. Every black hole has its own mini disk, which is prescribed by a Novikov-Thorne style emission profile. So it's a razor thin slab of emission in the equatorial plane. So this binary can be eccentric. It can have varying mass ratios. It can have different separation radii ranging from 100 gravitational radii all the way up to 1,000 gravitational radii. And so we did like a parameter study of how these model parameters affect the self-lensing feature. In total, we have 27 different models in the two papers that we published. But of course, sadly, like in the roughly 10 minutes that I still have left, it's of course impossible to go over all 27 of them. So I'll try to focus on the most important result that we obtained in this work. So first, let us all get a little bit more familiar to how these black hole images look like. So this is a nice visualization by Jeremy Schneepan from NASA, who did a similar ray tracing of an individual black hole. So what you see here is like this thin disk that is like orbiting around the black hole. There is lensing happening on the top and on the bottom part of the black hole. This is why you see this emission also above the black hole, which is here in the center due to the strong curvature of space-time. So there is some Doppler boosting happening as well. So the left side is moving towards the observer, the right side moving away, so it's enhanced. Additionally, there's this photon ring, which is a critical curve where geodesics start to orbit around the black hole and catch up more and more emission. So this is like typically also a strong feature within these images. And in the center is the black hole shadow, which is also known as the apparent size of a black hole on the sky for a faraway observer. And the size of this black hole shadow is very tightly constrained by general relativity. So measuring a black hole shadow, and if you know the mass from a different mechanism, would help to like constrain general relativity. And this is of course also like one of the main goals, for example, of the Event Horizon Telescope collaboration. So let's show one of the models that we produced. So this is a black hole binary shown at 87 degrees, where 90 means perfectly edge on, so perfectly perpendicular with the orbital axis of the binary. The binary has a separation of around 100 gravitational radii. It's an equal mass system. It's a completely optically thick system, which means that there is no photon ring. So the disk actually extends all the way to the horizon. So photons don't have the ability to orbit around the black hole for more than one time. And this is an image generated at a soft X-ray band. So if we then start to play this movie, it will become clear why it's called a self-lensing flare, because the binary self-lenses itself. So the foreground black hole amplifies the background black hole, and it hugs around the foreground black hole, creating like this Einstein ring like feature. So yeah, this is what it looks like. Well, these quasars are of course typically quite far away, so there seems to be no hope of course generating a real image of such an event, but we can still look at light curves. So, and this is, for example, an example for a viewing angle of 90 degrees. So this is perfectly edge-on view of the binary with the same parameters as I described earlier in the previous slide. So in this case, you see again that you get like this nice Einstein ring around the foreground black hole. So, and here on the bottom, I now also show the light as a function of phase in the orbit. This is like normalized flux. So initially, everything is just nicely quiescent. And at the moment these two black holes line up, there is this increase in the amount of emission that you observe. But additionally, like most of the works in the literature only show a single individual spike without substructure. And in our work, we actually found that within this flare, there is some additional substructure, namely like this dipping cell feature that we see in both of these flares. And this seems to happen when the focal point of your foreground lens moves over the ring-shaped feature of the black hole in the back. So as the focal point moves over the left, there is emission that it can amplify. If it is in the center on top of the black hole shadow, there is no emission to amplify anymore. And on the right side, it's back on this ring again, and there is like an enhancement in flux. So this made me thinking, like, does this dipping feature then also nicely correlate with the black hole shadow size? And that seems to be the case. So what we did is we measured the duration of the dip in our light curve. And if you know how long the duration is, and you multiply this by the total circumference of your actual binary, I got a number 10.4 times the gravitational radius. And as a person who was also active within the Event Horizon Telescope, this immediately started ringing all kinds of bells, because this is the black hole shadow size diameter. So there seems to be a very nice correlation between how wide this feature is and how large the black hole is on the sky. And this is interesting because this can potentially then be used to find black hole shadows that are unresolvable by current VLBI techniques, because we don't have to resolve the source spatially. We just need to resolve the light curve time-wise well enough so that we can sample it good enough to measure the width of this dip at high enough accuracy. But of course, this was a perfect example, and the perfect world doesn't really exist. Like, the odds of seeing the binary exactly edge on is of course quite slim. So what about if you're slightly further off the equatorial plane? So how does it depend on inclination? So these light curves, as a function of inclination, I show here on the right. So the red one is again perfect edge on view, 90 degrees, and then we alter it all the way to 80 degrees here in black. So as the focal point moves further and further away from the source, the amplification efficiency starts to drop. But additionally, also the focal point does not move anymore over this ring-shaped feature. And you start seeing that like the width starts to slightly shrink because you pass over the circle at a different altitude. So effectively your diameter becomes smaller. And around, what is it, like 87 degrees, you start to not go over this shadow-like feature anymore. So for this particular setup, we have like a window of like roughly like 3 degrees, that it could be possible to get some information on the fact that, one, there is a shadow, and two, like on its actual size. So we can also do some analytical estimates then. For example, if you take just the ratio between the shadow diameter and the circumference of the actual binary, this is like what I would expect this signal to look like. You can plug in Kepler's third law and then plug in the binary mass, the binary period, and the mass ratio. And then you actually also get the exact same number that we get out of our ray tracing simulation. So the size is nicely consistent with this simple analytical prediction. But this also means that we can plot how large the window of this phase, or how big the phase is as a function of orbital time. And as the orbit becomes wider and wider, the velocity drops, so the binary moves slower. So the focal point moves slower over the background image, and the window becomes larger as well. So for LISA, this would mean like if we go to like shorter and shorter periods, the dip will become narrower and narrower. But however, the inclination window also grows because the size of the black hole as seen by the lens becomes larger and larger as well, because these black holes are just closer by. So this makes it on one way easier to measure because there's a larger window for it to be observable, but on the other hand, we will need higher and higher time resolution to actually sample this light curve sufficient. Yes.
3 more minutes, or 2.5 by now.
2.5 minutes. Okay, that's perfect. So what about search strategies? So the inclination window is quite small, but if we look at the current sample of black hole binaries, they're typically skewed more to the high mass end, so like 10 to the 9 solar masses. So this dip would and they have periods of around a year. So if we plug all of these parameters in our formula, then like the dips would take a couple of days and the inclination window is a couple of degrees at most. So the probability of finding this dip in the current data, if you assume a uniform distribution of inclinations on the sky, is around 1%. So first strategy would, of course, be to just follow up on the current candidates that we have, which are 150. So who knows, there might be one in there already. And of course, like as was explained by Cheng earlier today, for Rubin's Observatory, LSST will see like 100 million quasar targets. So we could also just look at that sample and might be something in there as well. And additionally, of course, interesting for this audience is to look at pre-merger electromagnetic emission for LISA sources, which will then help in looking at these spikes for sky localization and might give even some information about the black hole shadow size. So there is some preliminary outlook, like we are currently looking with a grad student here at Columbia, Luke Krauf, at like how, because we're using the Stoy model, the simple analytical profile for the emissions. So what would happen if we use a hydro code, which actually tells us how the matter moves around these black holes to get a better handle on the spectral shape, on velocities. We will then also include the circumbinary disk as a potential blockage towards the inner part of the binary, add additional accretion variability to figure out if this feature still survives above the noise of all the accretion whirling around. And if we could maybe then use phase folding, for example, to get rid of the time varying features and just get the only time consistent feature, namely the self-lensing flare. Well, given the time, I will leave my summary and outlook up, but yeah, I think it's an intriguing mechanism that could potentially be useful for LISA for sky localization or graviton mass measurements, or even black hole size estimates for sources that are way out of reach by VLBI techniques by the Event Horizon Telescope. And I'm happy to take any questions either now or via email.
All right, thank you very much. And so let's see if there are any questions in the chat. Raise your hand in the participant list with the raise hand button, or questions from the live stream. I think there's still only clapping hands for now. Anybody? Jordi and I have been having some conversations about this already, but let's still see if there's anybody else. Okay, if not, then I'll go. So in the 150 candidates that you have now, do you think there's any inclination bias?
Yeah. Yeah, there is inclination bias because they are found via their periodicity. So there should already be some Doppler boosted signal, right? So these sources are typically viewed more edge-on than phase-on because they are found via Doppler modulations. So this percent number that I gave is a little bit on the pessimistic side, even like it could be higher, given that these are found more closer to edge-on than phase-on.
That's good.
Yeah, but one thing to maybe mention is also like there is also of course mass ratio here, so that might like make things harder again, because I only showed here like equal masses. Like if the black hole becomes smaller on the sky, it will also be harder to observe it again. So there is some competition with a lot of different things.
All right, well, I think we've had this discussion about equal masses. You know my opinion on equal masses. It's a very bad idea. I see no other hands. I'm sure that's not because, well, maybe it's because the talk was so clear or everybody already read the two papers, then that's the other option. All right, let's wrap up here and thank all the speakers of this session. We went from accreting white dwarfs to supermassive black hole binaries to quite detailed things about lensing, etc., etc. I certainly enjoyed it a lot. Thank you all for keeping well within time, which means that we end this session even 10 minutes before the end. We have a slightly longer long break. I wish you all a good break. I hope to see you back at the other sessions today, which start 8 o'clock our Central European summertime, which is 2.5 hours from now. Rona, are there any other technical or other things we should say?
No, I am pretty much the same. I was just going to thank you for chairing so well, and thank all the speakers again. All the talks were brilliant, and I hope the audience enjoyed them all. Yes, so enjoy the 2.5 hour break. The plenaries tonight are a bit lighter and less technical and should be enjoyable as well. So see you all back then.
Bye-bye.
Thank you. Bye.
Thank you.